prove that the square root of 2 is an irrational number. So first, what is this irrational number that the problem is evolving around? So it's probably simpler if I say what a rational number is first. So any number x is rational if and only if it can be written as a over b, where a over b is the most simplified fraction, and b are relatively prime integers, and b is non-zero. So it sounds like a big mouthful, right? That relatively prime integers, but all that means is a and b are integers, and the greatest common divisor, GCD, of a and b is 1. That's all relatively prime means. So using this definition of a rational number, we can say if something is that doesn't fit one of these restrictions, say a and b are both integers, however they're not relatively prime, well then you could say that it's not rational, and if something is not rational, you can say it's irrational. So I'm going to prove that it's irrational by proving by contradiction, which means we're kind of contradicting our idea or going against our idea by saying or pretending that the square root of 2 is a rational number, and then proving that it's not possible for that to do that. Because, well, like because how about this? Since we're proving something that's irrational, that means it's not right. And that has nothing that explains not true stuff. So it's kind of hard to prove something that's not true, which means we can pretend that it is true, because then we got facts, we got formulas, we got everything to back us up to prove that it is not true. So we're kind of going in circles there. So assuming that the square root of 2 is rational, then the square root of 2 should be written, or should be able to be written, as a over b. And that square root, complicated, get rid of it. So square both sides, and we have 2 equals a squared over b squared. Multiplying by b squared, we have 2b squared equals a squared. So a little, okay, I'm just going to tell you what to do here. It's a little hard to think about it. I'm going to convert b squared into b times b, because that's what b squared is, b times b, equals a squared. So now I'm going to divide by b, and why did I separate that other b is because then, first of all, I guess something more relevant. Second of all, well, I know that because b up here, because again, we're assuming that the square root of 2 is rational, then b is an integer, a non-zero integer, which means 2 times b is also a non-zero integer, and then a squared over b squared is a non-zero integer. So that means that b can divide into a squared evenly, or in more mathematical terms, we can say b can divide into a squared, and that's just a fancy way to write a fraction. A denominator, numerator, denominator, and then numerator. So we have this piece of information, and now we're going to have to find a second piece of information. And we could get that by thinking back to this square root of 2. Because the square root of 2 is a positive number, right? And if we're writing a positive number in terms of a fraction, that means we can either have a negative over a negative, so a and b are both negative, or we can have a positive over a positive, both a and b are positive. And, well, since we're going to be squaring, first of all, a and b, that means we're going to end up with a positive anyways, and second, positives are just plain easy to work with. So I'm going to assume, again, a lot of assuming, that a and b are both positive. Because, again, you can do it with negatives, but, again, do it with positives. So if a and b are positive, that means b is greater than or equal to 1. That's what positive means. But that equal, we can just get rid of that because b cannot be equal to 1. Why? Because if b were equal to 1, that means the square root of 2 would equal a over 1, and then a would be the square root of 2. Problem is, because the square root of 2 here is rational, then a and b have to be integers. And, well, the square root of 2 is obviously not an integer. So b cannot be equal to 1. So b is greater than 1. So how does that help us? B is greater than 1. Why? Like, why do we need that? Because, well, fundamental rules, like basic rules of math, tell us that any integer greater than 1 must have at least one prime in one prime greater than 1 in its factorization, which sounds like a mouthful, but really all it is so we have a number greater than 1. Pick a number. 9, for example. That number must have a prime in its factorization, or not factorization, as one of its factors. So, well, 9 is 3 times 3. Guess what? 3 is a prime. And even like other numbers, like 7, for example, well, 7 is 1 times 7. 7 is a prime. So any number greater than 1 must have at least one prime as one of its factors. So, well, of course, a prime, well, 1 isn't a prime. So everything from 2 up, or well, not everything, all primes are 2 or greater, which means our prime, which I'll name P, is greater than 1. Well, if P has to be, is a factor of B, that means P can divide into B. Why don't we just have a kind of like a little equation? Not really an equation, but kind of. Something like that. Again, P can divide into B, right? B can divide into A squared. Well, I can just get rid of B, like for example, just like how if you had 3 equals X equals Y, you can just get rid of X to see that 3 equals Y. Same thing here, because we can just cancel away the B, and we'll just have P can divide into A squared. Well, that's a new piece of information. And, well, if P can divide into A squared, it makes sense, or in fact it has to, that P can divide into A, right? Since if I can divide into the square of something, I can divide into that something. So that leads us to say P can divide into A. P can also divide into B. That means P is a common divisor of A and B. Well, if P is greater than 1, well, now it's really obvious that what we should do. The GCD, the greatest common divisor of A and B, lowercase b, B is greater than or equal to P, and P is greater than 1, and again, cancel away the P, that means the greatest common divisor of A and B is greater than 1, and because we said all the way at the beginning of the video that A over B has to be in simplest forms, that gets rid of any possibilities like 25 over 5 and some other person saying, oh, these two numbers are not relatively prime, however, they make to be 5 and 5 is rational, so this formula is totally trash. No, it's not. A over B has to be in simplest form, which means now, because of that, that gets us to the last step of proving 2 is not rational, because, well, A and B aren't relatively prime. Sure, they can be integers, but they are not relatively prime. So x, which in this case is square root of 2, cannot be equal to A over B according to our restrictions, which means if the square root of 2 is not rational, well then if something's not rational, then it has to be irrational.